Hello everybody and welcome. Today we are going to look at sequences and summation notation. This is from chapter 10.1. We're jumping around a little bit in the book, but it's going to make sense once we get into it. All right, so what the heck is a sequence? Well, informally, a sequence is an ordered list of numbers. Here is an example of a sequence. 2, 3, 10, 12, 15, 18, 20, done. Now this happened to be an increasing sequence. You don't have to be increasing. They don't even have to have a rule. You can just be an ordered list of numbers. You can have positive numbers, negative numbers, fractions, anything you want in your sequence. Just an ordered list. But what differentiates a sequence from a function is that it's a specifically, and this is where we get a little more formal, a function whose domain is the set of positive integers. What do I mean by that? Well, I mean that there's a specific first term, second term, third term, fourth term. So the number of the term is like the input, and the actual value of the sequence is like the output. So the domain is the number of terms, or what the number of the term is, and the range is the output. So in this sequence, I borrowed this from the book, the sequence is 1, 1, 2, 3, 5, 8, 13. But that one is the first term. This one is the second term. You can have terms repeating. That's something else that happens in here. This is the third term, etc. And so sequences, what makes a sequence is that it has specifically defined terms. And you could say that the inputs start at 1 and always go up by 1. The first term, second term, third term, fourth term, fifth term. That's what makes a sequence. Sequences can be finite or infinite. Right now we have two finite sequences. If I go back up to the example at the top and just add a couple more terms, -3, 11, -1000, 2, and I could just write, if I want to indicate that this goes off forever with, no necessarily repeating pattern, you can just include an ellipses, a little dot, dot, dot. Like that. So that's like the basic idea of sequences. But of course, without any sort of predictability, it's hard to manage them. So we start to put in things like rules for sequences. And that's what we're going to get into now. So we think about a generalized sequence, just, in its most general form. It's a set of numbers. And that is why we might name a sequence A sub n, and we include these braces when we're talking about the sequence as a whole, because it is a set, and these are the objects that say we're looking at set notation. But an consists of terms, and we write that the first term is a1, the second term is a2, the third term is a3, the fourth term is a4, etc. Now, if you want to skip a bunch of terms in the middle of writing a sequence, you can include an ellipses. But ellipses don't mean you have to go off to infinity. You can just say, all right, we've skipped a couple terms. Let's go assume that this is a finite sequence. Maybe there are n terms. Well, then I would do the term before the nth term would be term a n minus 1. I don't know how big n was. It's just some unknown constant. And then the last term would be a n. And so that's how you would write out the terms of a sequence. This would be the nth term, first term, etc. And that is why the brackets are important, right? If I write an without the brackets, I'm talking about the actual last term. If I write an with the braces, I'm talking about the whole sequence as a whole. Sometimes that can get a little messy or confusing, depending on the problem, but just be careful of those. All right, now say I want to list the terms of a sequence from a rule. So, right, we said sequences don't have to have rules, but most of them do, especially when we're thinking about math problems. In terms of math problems, there's going to be some kind of pattern to these numbers that are coming up. So let's list the first 5 terms of each sequence. So our first sequence is an is equal to 3n minus 1. So we could say, okay, a1 would be the first term, and then the equation is saying, hey, look at this little n, and use that in a formula to figure out what the actual term would be. So a1 would be 3 times 1 minus 1, which is 3 minus 1, or 2. So the first term is 2. A2 would be 3 times 2 minus 1, which is 6 minus 1, or 5. A3 would be 3 times 3 minus 1, 8. It looks like I'm going up by 3s, kind of, which maybe makes sense. A4 would be 3 times 4 minus 1. And the fifth term, A5, would be 3 times 5 minus 1, or 14. So those are the first 5 terms of each sequence, 2, 5, 8, 11, 14, or of this sequence. For the next sequence, again, I have AN. By the way, it doesn't have to be A. I could call this B or D because there's fractions there. A is just a convenient number or letter, just like, you can use F or G or H when you're talking about functions. So this one's a little goofy because we have a -1 to the n and we have some fractions. But let's work it out. So A1 would be -1 to the first over 1. That's just -1. A2 would be -1 squared over 2. Now, -1 squared is +1, so this is going to be 1/2. A3 would be -1 to the third over 3. Well, -1 to the third is back to negative, so this is -1 third. You can kind of start to see the pattern. A4 is -1 to the fourth over 4, which is +1/4. And A5, -1 to the fifth, that'll be -1 over 5, so -1/5. And if I wanted to write those terms out a little better, I could write it as, in a row. Just like that. So always follow the rule. It's much like equations. They don't have to behave in a linear way. They can have these goofy fractions going on. They can be just as complicated as any other kind of equation. And really the main difference is you're using an n instead of an x because your domain is just the integers or the numbers instead of all real numbers. So one other way to look at sequences is to give what's called a recursive rule, or work from what's called a recursive rule. Recursive means like a word is recur or happen again or go over on itself. So this is like a looping rule that refers back to itself. A recursive rule always has 2 parts. It has a part where they tell you a starting value, and then a second part where they tell you the actual recursive rule. That's different from the general form equations we saw earlier, where they just told you one single equation and you started with 1 and you plugged in child. Here, it's telling us where to start, and then in the recursive rule, I actually need to move the U up here, we see some goofy terms. We see AN, which is basically saying your next term that you're trying to write, and we have this AN minus 1. This is saying n minus 1 would be the term before AN. So this is the previous term. And then there's, of course, some numbers and operations that tell you what to do with the previous term. So this rule is saying, here's what you should do to the previous term to get the next term. So this is basically saying 2 times last term minus 1 will equal next term. And if we say it in a sentence, so that's kind of weird to do. So let's list that out. Well, the first term would be 2, because that was A1. That's where we start, is with that initial condition they've given us. Then to get the next term, I take the previous term, which is 2, multiply it by 2, I get 4. I take away 1, I get 3. So the next term would be 3, because that's 2 times 2 minus 1. Now, to get this term, I'm going to go to the 3 and use that as my previous term. So we'll do 2 times 3 minus 1, 6 minus 1, and get 5. So I have 2, 3, 5. Let's keep going. 2 times 5 minus 1 is 10 minus 1. That's 9. 9 times 2 is 18 minus 1 is 17. So it started out pretty tame, 2, 3, 5, but now I'm up to 9, 17. This thing's actually going to grow pretty fast because I'm doing this doubling. We'll do one more term. 17 times 2 is 34, minus 1 is 33. We can see that this is actually growing pretty quickly. I don't actually know the closed form rule for this. There might be some quadratic equation that could give me the general term, but I really just have I don't feel like finding it. I really just have the recursive form. And that's enough, to list the terms in a sequence. Of course, recursive form is kind of nice because it's very intuitive. It says, all right, here, you've got this term. Here's what you do to get to the next one. But turns out that general forms are actually more useful, right? Like, what if I wanted the 100th term? Well, I don't really want to write 100 terms to get to the 100th term. I'd like some sort of closed form, happier equation. So we don't use recursive rules a lot in math when we're looking at sequences. But they're better than having nothing. They can help you write a sequence. They can help you understand a problem. And sometimes there might actually be the only rule that works. There's some famous sequences that they really are best defined recursively. So it's important to be able to recognize a recursive rule and understand it, even if they're not as useful necessarily as other kinds. Let's do an example of both a recursive and a general rule for a sequence here. So finding a rule for a sequence can be complicated. You have to sort of use your logic, especially because you don't know if this is going to behave in a linear way or a quadratic way or an exponential way or a mix of those. So you just kind of have to use your intuition. So first, I can say what I know. I know that the first term is 12. And then I can kind of look for a pattern. I'm going from 12 to 6, so I could be, actually it's going from 12 to negative 6, and then up to 3, and then down to negative 1.5, and then up to 0.75. So there's a lot of stuff going on here. The first thing I would notice is that it feels like the negatives are not really part of the same pattern as what's going on with the numbers. I feel like I have a positive, negative, positive, negative, positive, and the next term would probably be negative. So I'm going to sort of ignore the negatives for a second. And I recognize that maybe, 12 divided by 2 is 6, and 6 divided by 2 is 3, and 3 divided by 2 is 1.5. So ignoring the negatives, it seems like I'm dividing by 2 and changing the sign. That seems like what's happening in this sequence. So how could I write that? Well, let's write this recursively first. A1 is 12. The next term could be the previous term, an minus 1, divided by 2, and times, well, how do you change the sign? Multiply it by negative 1. We could even, group the numbers together and make this negative 1/2 times the previous term. So that's a recursive rule. I have the first term, and I'm describing what to do to get to the next term, multiply by negative 1/2. So that was our recursive rule right here, recursive rule. Now to find the general rule, and this is a type of sequence that you haven't really officially seen yet, but I think you can kind of see what's going on. We're dividing by 2 every time, but I'm going to say we're maybe multiplying by negative 1/2 every time, aren't we? And that's what our recursive rule says. We're multiply by negative 1/2. So to go from the first term to, say, the fourth term, I've multiplied by negative 1/2 3 times. So a general rule might be something like, okay, well, we can start our first term. You can just use the actual number for the first term here. I could say times negative 1/2, but I need an n. I need an input variable. Well, n should be the number of times I've multiplied by negative 1/2. So for the first term, I've multiplied by negative 1/2 0 times. So I can't just put an n there, because that would be I start n always at 1. But what if I did something like n minus 1? So that when in the first term I'm multiplying by negative 1/2 0 times, So it's just a 0th power, 1. Second term, you're multiplying by -½ one time, 2 minus 1. That would work. And this is, in fact, the general rule for this sequence. So there will come a time where, for a sequences like this is called a geometric sequence, we have an official format for the general rule and how it looks. For now, just come up with something that works. Use exponents if you need to. If you have something that's alternating, use a negative inside of an exponent. That will cause that alternating power, I don't know, however you say it. And just use your brain, use your logic. All right, to close this video, we're going to talk about something that's not really sequence related, but shows up in sequences from time to time, and it is part of this section, and that's called factorials. Sometimes you see them in sequences, and they're very, very useful in probability and counting. And factorial is that exclamation mark you sometimes see before, or actually not before, but after a number. So, 5 with an exclamation mark is pronounced 5 factorial. And what does factorial mean? Well, it's in the word factor. So I have 4 factorial here. 4 factorial is a command that's telling you, the reader, the writer, to do this. 4 times 3 times 2 times 1, and stop. So it's not like a sequence where you're listing the numbers, you're actually multiplying them together. 4 times 3 times 2 times 1, stop. And then you can usually multiply these with some smart grouping. 4 times 3 is 12, times 2 is 24, times 1 is 24. So 4 factorial is 24. You can check this out. We could do 6 factorial. Well, that would be 6 times 5 times 4 times 3 times 2 times 1. We can be a little smart here. I already just found 4 times 3 times 2 times 1 is 24. And 6 times 5 is 30. So again, we can group and do whatever 30 times 24 is. 720. Whoa, that got big really fast. So that actually is a really cool thing about factorials. They grow incredibly quickly. Here's our factorial, telling you a cool fact about them. That is that 10 factorial seconds is actually exactly 6 weeks. Wait, think about that for a minute. 10 factorial can't be that big. But let's grab our calculator and take a look. 10 factorial, you could do 10, and then factorials in your math, probability, option 4. Big number. All right, but that's that. If that's seconds, we could say, okay, divided by 60 seconds in a minute, divided by 60 minutes in an hour, divided by 24 hours in a day, 42 days, and divided by 7 days in a week, you get 6. So that's why 10 factorial seconds doesn't seem like a lot, but it would be 6 weeks, if you laid them end to end and just never stopped counting. And this is from our book, but it's a really cool table of just how fast factorials grow. So here's 10 factorial we were just looking at. And then every time you go further down the list, you're multiplying by one more number bigger than 10. So you're always going to add like at least 1 decimal place, if not more. And by the time you get to 20 factorial, you get something in the, I don't even know, that's billions or trillions. It's big. Something big. And you can play this on your calculator. You know where the button is now. That's a really good way to get overflow errors on your calculator if you want to press things to the end. So that's factorials of numbers, is just multiply everything beneath them. Oh, by the way, 0 factorial is defined to be 1. I know you all think it should be 0. It's 1. We can talk about it more in class, but it is 1. Going back to this, if I have to write something more general, like n factorial, so that would just be n times n minus 1, right? Because if I don't know what n is, I just have to keep writing like, oh, well, whatever is 1 less than that is n minus 1. Whatever's 1 less than n minus 1 would be n minus 2. And n minus 3. And here I'm going to have to use our friend, the ellipses again. So do 3 little dots. And then we say, all right, we are going to conclude the pattern, 3 times 2 times 1. Something like that. So n factorial you can think of as that generalized term if you need it. Let's actually try that out. So write the first 4 terms of the sequence. an is 3 to the n over n minus 1 factorial. All right, so we have a sequence now, so we can just let n be 1, 2, 3, and 4. So if n is equal to 1, we have 3 to the 1 over 0 factorial, 1 minus 1. So 0 factorial is 1, so this is 3. If n is 2, then this would be 9, 3 squared, over 2 minus 1 is 1, so that's 1, so that would be 9. If n is 3, that would be 3 to the 3rd over 2 factorial. Well, that's 27 over 2. 2 times 1. Nothing reduces here. And finally, if n is 4, that will be 3 to the 4th over 3 factorial, which is 3 times 2 times 1. So I'm actually going to write this out as 3 times 3 times 3 times 3 over 3 times 2 times 1, because something cool is about to happen. It actually reduces out to the same way, 27 over 2. And that might feel a little weird, like, what? Why do we get the same value? But that's just what happens, because we added a factor of 3 to the top and bottom, 1 from the exponent and 1 from the factorial, and they just reduced themselves back out, giving us sort of the previous term. If you did more terms, it would start to grow again. But this is goofy stuff can happen with sequences, especially when factorials and exponents are involved. All right, another example with factorials, and this should close out this chunk of the video, simplifying expressions using factorials. And I'm actually going to use that same idea we just used in the last problem of writing things out and simplifying without multiplying. Keep your numbers small, always. So 6 factorial over 4 factorial 2 factorial, which is, by the way, the number of ways to select 4 things out of a group of 6 if order doesn't matter. Counting. But for us, just think about it as 6 times 5 times 4, 3, 2, 1, over 4, 3, 2, 1, 2, 1. Whew! Feels like a lot of similarities, doesn't it? So 4, 3, 2, 1 can automatically reduce out. And while we're reducing, hey, why don't we reduce a 2 and make that a 3? Now notice that pretty much everything in the denominator has moved out, and this is actually just equal to 15. If you want to be even saucier about it, you don't have to write the 4, 3, 2, 1. You can just say 6 factorial is 6 times 5 times 4 factorial. Right? That's what it would be, 4 times 3 times 2 times 1. And we have 4 factorial down here times 2 factorial there. And you could just cross them out in that way as well. Then you just do 30 over 2 and get 15 again. All right. So 15 again. And what if we had these general terms? Now, this is a little wackier, but let's use this idea of just writing things out. So n factorial is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. I'm using parentheses there just for consistency, I guess. N plus 2 factorial is n plus 2. Well, what's one less than that is n plus 1 times n minus 1. Oh, and it's starting to have the same pattern. So in this case also, everything after a certain point starts to cross out, and you just get 1 over n plus 2 times n plus 1. You could multiply out, but I think it's probably nicer to leave it in its little fractional form. It kind of looks like a little rational function now. You could also do this a little more simply. You could say, okay, this is n factorial on top, don't write it out, and just be n plus 2 times n plus 1 times n factorial, instead of writing out all of those last terms and then just cross those things out. That'd be another way to think about it. So simplifying expressions with factorials, whether you have numbers or variables, just write it out and look for things to cancel. And if there's no fractions, then nothing will cancel, and you probably just write it out. But most of the time, these will have fractions to cancel. All right, folks, that's going to cut it for this video. Stick around for the next one. We're going to learn about summation notation. See you soon.